So let's see. I want to start out by talking a little bit about the final exam. Final exam is 3 hours. It's next Wednesday for MIT students. And it will be next, is it Wednesday or Tuesday night? It'll be Tuesday night for Singapore students. Okay, and at MIT it's of course 9 to noon, and in Singapore I believe it is 7 to 10 or 6 to 9. I think it's 7 to 10 is what we decided. So for that, so the announcement is up on the web page for the final. You may bring 2 8.5 by 11 crib sheets. Okay, handwritten crib sheets. Okay, no photo reproduction allowed. And it will be more like quiz 1 than it was like the final, although there will be a little bit more creativity asked on the final than there was on quiz 1. So it's pretty much 80% of it is mastery of material, and do you understand things well enough to be able to manipulate things. So, but not a lot of the kind of creativity that we had on the take-home exam, okay, where you rack your brains to figure out how to do something. It will cover material from the entire course. There will be some additional stress for things that have not been tested, like network flow, and for things where people have been I think weak when we have tested it in the past. And the one conspicuous area of weakness was shortest paths and graph algorithms. Okay, so you should know the difference between breadth first search, Bellman-Ford, Dijkstra's algorithm, DAG shortest paths. Those are all single source problems. And the various algorithms, the matrix multiplication algorithm, the Floyd-Warshall algorithm, Johnson's algorithm for all pairs shortest paths, and have some understanding of how shortest paths are used in network flow to get bounds on the performance of network flow. Okay, so there's a whole bunch of stuff there that I think people are generally weak on and which I intend to test a little bit more. But in addition, we will hearken back to the beginning of the term and ask you to solve recurrences. Make sure your knowledge of sorting and basic data structures, range trees, interval trees, red-black trees, okay, binary search trees in general, and so forth is, you understand it. Amortized analysis, competitive analysis, and so forth. That all those things are, you're responsible for as well, and we will test those things. Okay, in 3 hours, you can test a lot, but it will be more a question of basic mastery than of any particular cleverness. However, the level of mastery is not do you remember something, but do you understand something well enough to be able to apply it. And there's 2 ways to apply something. One is to use it as a subroutine. Okay, that's one way you can apply something. And the other thing is to understand how it works so that if you modify it, it will behave better. Okay? So, for example, understanding Dijkstra's algorithm that uses a priority queue and what the impact is of using different types of data structures to implement that priority queue. Okay, you have to understand the structure of Dijkstra's algorithm in order to understand those things, just as an example. Minimum spanning trees, greedy, dynamic programming, all that stuff. Okay? So any questions about the final exam? Okay? Who's ready for this semester to be over? Yeah. Okay. Boy, this has been a rough term. Okay, for everybody, I think. A very rough term. So today's lecture will be, quote lecture, has 3 parts. First, we're going to announce some of the contest results. Oops. Neil. Yeah, Sid or Neil, right. We're going to announce contest results, so Bob is going to do that. Then I'm going to talk a little bit about what's next in terms of follow-on courses to this course. If you discovered that you were interested in the course content, there is a lot of stuff in algorithms. And we'll talk a little bit about what the courses are that you might consider taking in the next few semesters. And then we will do the annual course evaluation. Who's doing course evaluation? Is it Jordan? Okay, hi. So we'll do that at the end of the period, and then if there's a little bit of time, I'll show you one of my favorite algorithms. Okay. So, Bob, you want to?
Yeah. Okay.
Here we go. Just a second. Gotta wire you up.
All right. Okay, well, we had a lot of really smart and creative algorithms this year, a whole bunch of different search techniques that showed up in the solutions. And it turns out it was a photo finish between first and second place. So we have a bunch of prizes to award. Fourth place goes to Oliver Cossett, who I don't believe is here today. But he gets a great sliding block puzzle from Binary Arts. I'm told this is an extremely difficult puzzle, even though it looks simple. Okay, and hopefully I will meet him during office hours or something tomorrow. In third place, we have Tushara Karanaratna, if I'm pronouncing that right. And here we have another great sliding block puzzle from Binary Arts. This is one of their newest puzzles, Roadside Rescue. It's actually a 3D sliding block puzzle because the cars interfere with the natural block sliding. Congratulations. And first and second place, it was very close between. One of the algorithms had the cleverest search strategy, and the other algorithm had the best optimized position comparison. So it had the edge on raw speed. And it turns out that in this case, raw speed won. This one used a lot of clever hashing, Zobrist keys, all sorts of neat stuff like that. So the first runner-up is Li Shuai Cheng from Singapore. And he is not here to accept his prize, but his prize is the special puzzle, which was one of the puzzles presented at the year 2000 International Puzzle Party in Los Angeles, which is a clever sliding block puzzle. It's called Slide Trombones for various interesting reasons. Also $50, and also this nice certificate. Okay. And grand prize goes to Eric Suliang Ho for his really fast algorithm. Is Eric here? Okay. Well, I know he worked really hard on it. Oh, yeah. Great. So yes. So here is your certificate, and you also get a custom-made puzzle, which is yet to be produced. We'll choose one of the designs that your program produced and have it custom-made for you, and also $100, which we will arrange.
The issue with $100 is that it has to do with the IRS. The tax people, they want to deal with, so we have to negotiate with you whether you would rather accept a gift or with the cash. And maybe the gift can be a certificate at, say, Galleria or something like that. So I think we'll work this out. Anyway, it's perfectly legal for those people who are listening on tape.
And I want to show off some of these winning entries.
Great.
Get this projector going. We have the lights. Yeah. So this is a puzzle that Li Shuai Cheng's program designed. It looks pretty simple. The idea is to move this yellow piece here over to where the pluses are down here. However, it turns out that this actually takes 43 moves to do this, amazingly enough. And let's see what they look like. So this puzzle and this solution were both generated by Li Shuaicheng's program. So it's actually rather tricky to get it over there. This is the minimum length solution. I verified this. Okay. And this one was generated by Eric's program, and it takes, I think, 46 moves. In this case, the problem is to get this yellow block here down to the lower left, which it's very close to, but as it turns out, you have to move it quite a long way away before you can get it back. All the way to the opposite side of the board. So this would be quite a difficult puzzle to try to do by hand. Okay. Okay, thanks everybody for entering. Had a lot of fun with this contest, and I hope you all did too. And that's it for the contest.
My fountain pen, however. I have to arrange that later. Okay. So, what's next? Assuming that anything is next, I haven't drilled the love of algorithms out of you during the term. So, MIT is full of a lot of great courses, and so I want to describe some of the ones that follow on to this course, for which this course is, for almost all of them are prerequisite. Not all of them, but most of them, this course is a prerequisite. And so having taken this class, we have a wealth of courses, and the people in Singapore can listen to a little bit about what the topics of these courses are, and one of them they will be taking next term, but some of the others will be they'll have to, there's probably other courses in Singapore that correspond, and they can talk, people in the SMA program can talk to Professor Lee about them. So probably for most people, the most natural next course is either 6045 or 6840, which are on essentially the same topic. This one's called Automata, Computability, and Complexity. And it's an undergraduate course taught in the spring. And the other one is called Theory of Computation. And it's a grad course taught in the fall. Okay, and both of these courses are courses that, in some sense, make you educated as a computer scientist as opposed to trained as a computer scientist. Okay? So the difference is less on what are the specific skills as they are on understanding computation and the difficulties of solving particular types of problems. So most of the courses we've looked at in this, this term have been problems where we could express the running time as a polynomial in the size of the input. Okay, so things like n squared or n cubed. Okay, so, something to a power, n log n. They're all bounded by a polynomial. And we've not been too excited when we get something that's exponential time. Okay, if it's something like 2 to the n, that's not much of an algorithm. Okay? Well, in this course, you study a lot of the properties of problems that make them easy or hard to solve. You discover that there's some problems that cannot be solved by computers. Some problems you can state a problem where for a given input, there is no program that computes the function that you want of that input. The most popular or known of those problems is the so-called halting problem. Because you're given an encoding of a program, and you're asked if you run this program on a particular input, will it eventually halt, or will it go into an infinite loop? Okay? And it turns out there is no program that can take a description of a program, that is the code for a program, and an input, and tell you whether or not the program, when run on that input, will halt or not. Okay? That's an impossible thing, and they go through the proof of that. They also talk about the issue of universality. Universality is one of the most powerful notions. It's sort of the birth of computer science by Alan Turing, was his discovery of the notion of universality. And what that means is, if I say, well, there's this great big computer out there, a big Silicon Graphics Origin, 11 million or whatever, okay, some great big monster supercomputer, what things can it compute that your, Palm Pilot, if it had enough memory, okay, could not compute? And the answer is, it can't compute anything more. It might be able to do it faster, okay, but it computes, the things it can compute are exactly the same things. And the reason is because I can write a program on my Palm Pilot which will simulate that machine. Okay, and that's the basic notion of the power of computing, that you can actually simulate other machines. And so therefore a single machine, okay, becomes is universal, and you can take that single machine and program it rather than having to build a separate machine for every application that you have. Okay? And a result of that is the tremendous economic impact of universality is it means you can take a standard processor, okay, and optimize it like crazy rather than having to have a separate design for a dishwasher or a microwave oven or your desktop workstation or your Palm Pilot. In principle, you could use exactly the same processor for all those applications. Okay, and so therefore there's a big economic incentive to be able to replicate those things. So universality is a really important idea. Another important idea in these courses is the notion of a formal language. So these are the types of languages that we program computers with. Okay, and you learn a lot about formal languages, which has a great application to compilers, to the design of hardware, because it turns out certain formal languages can be implemented directly in hardware with a particular type of primitive machine called a state machine, finite state machine. Okay, and you find finite state machines all across your studies. I'm sure some of you have seen it already in 6004. Okay, so the foundations of finite state machines are taught in this course, okay, because they help you to understand all these other notions I'm talking about. And these courses tend to end with the issues of complexity theory. Complexity theory is really the center of it is the work on NP completeness. There's some problems that are computable. They do have answers, but we don't know any efficient algorithms to solve them. Okay? It's really an unfortunate situation, and people may have heard of the P versus NP problem. Okay? We don't know any algorithms to solve these so-called NP-complete problems, but we can prove that if somebody had a way of solving one of them, they would fast, they would all be solvable fast. Okay? So I mean, really quite remarkable property that even though we don't know how to solve any one of them, if you could solve any one of them, then they're all solvable fast. An example of this problem, this type of problem, is the so-called traveling salesperson problem, okay? Which is the problem of you're given a matrix, say, of distances between cities. And you have to visit all the cities on a tour and end up at the beginning spot such that your cost of travel is minimized. Okay? And it sounds like the opposite of a shortest path problem in some ways, because you're trying to find it sounds like a shortest path, and you're trying to find a path through everything. It also sounds like a minimum spanning tree problem. Minimum spanning tree is almost the same problem, except you're connecting it up with a spanning tree. Here, you just have to connect it up with a cycle. But it turns out that this is a really hard problem to solve. Okay? And then part of what you get into are issues of approximation algorithms and so forth. And you'll find some of these topics at the end of the algorithms textbook that you have. But that, I would say, is a rather incomplete presentation. It's a lot of material and a lot of very dense and very fast. And one would do much better to go through the development that's in these courses. Now, some people, when they teach this course, actually do teach NP completeness in the space of about a week. My experience when I've done that is the students are left with the stuff spinning, and they say, oh, I want to see that stuff again, and they never go on to these courses. So I prefer to do things like network flow, which I think leads much more naturally from the stuff that we've done. Or sometimes I teach some parallel computing, or sometimes we do more geometry. We do a whole bunch of different things in this course, depending upon who's teaching it. So these, I think, are the two most natural courses. Let me just tell you something about, in particular, 6045. For those of you who are concerned about the fact that you have a lot of classes with a lot of people in it, 6045 is generally a relatively low enrolled course. So it's really nice. It's really kind of intimate. It tends to have between 30 and 40 people in it, which I used to think of at MIT was a big course, but not in today's age. Okay? So this is actually quite a nice course. Excellent book. I'm not sure who's teaching it in the spring. Don't remember. I think Ron Rivest has been asked to teach it, but I'm not sure that he's agreed to. I think he's negotiating for. I mean, because there's a bunch of things, but anyway. And Rivest is a great teacher if he does teach. He hasn't taught in a while. So, so any questions about these courses? I mean, this is just great. I think is great material. Practical aspects of this, immediate practical aspects, no. In terms of having a really good picture and perspective on computer science, on AI, on systems, etc., wonderful, wonderful course. But it's sort of good for you in the more philosophical sense, okay, than it is good for you in terms of, well, here's a skill that I'm going to apply tomorrow in my programming problem. Okay, there are a few things like that, like in particular with finite state machines, but really it's much more, do I understand how the world operates? Okay, and this is a great course, and both of these are very well taught courses. Okay, any questions about those? Okay, let me. There's another course that's. This is a course offered next term, 6338. Parallel Scientific Computing. And in fact, the SMA students will be taking this course. So let me explain a little bit about what's in this course. This one does not technically have 6046 as a prerequisite, but if you had 6046, you will have a big edge on people who have not had it. The other prerequisite for this course is 1806, which is linear algebra. Okay, so this is a course that basically combines algorithms, linear algebra, and modern parallel architectures to build programs whose performance works as a function of the number of processors. We haven't really seen much of that in this course. Okay, but sometimes I teach parallel computing in this course because it's my own research area. This time I said, okay, we're going to teach Eric's research area a little bit more. So we did range trees and some computational geometry and so forth. This course is taught by, this spring will be taught by Alan Edelman, who's a professor in the math department and in Laboratory for Computer Science. It's a great course, wonderful hands-on experience with a lot of different parallel environments, use of MATLAB, analysis of programs for doing a wide range of both dense and sparse matrix calculations, and teaching you a lot about floating point, which is something that generally gets very light treatment in the computer science curriculum generally. But in the scientific computing environment, it's extremely important that one knows how to do floating point operations properly. And most people, whether they know it or not, are going to end up with some sort of floating point problem in the future, because floating point doesn't represent real numbers perfectly. And so understanding some of the basics of floating point is a skill which, you'll find just will go into the future with great advantage when people around you, don't know what's happening to this code. This, if you're controlling a machine, often you're using floating point. Okay, if you're looking at any kind of signal processing application or image type of problem, okay, there's a huge number of places where accounting is used and where round-off error can cause your program, even though it would work perfectly if you had real numbers, goes all to smithereens if you use floating point numbers. Okay, and so there's a lot of techniques for understanding how those things work. But the focus is more on the architectural sorts of things. So people interested in computer architecture is a great course, okay, because they go through distributed memory machines, collections of workstations, internet type things, modern SMPs, so-called symmetric multiprocessors. Okay, talk about a lot of the issues with that, multi-threading. Okay, all those sorts of things are covered in this course. Okay, another course which is a real fun course. Actually, MIT is such a candy store of courses, especially ones that related to algorithms. Okay, computer graphics. This is a graduate course taught in the fall. Okay, so this is how do you represent things on a screen, doing things like manipulation of images. How do you do shadows, lighting, shading, hidden line removal? Okay, lots and lots of great topics about rendering of objects. Okay, and this is the sort of thing that if you want to go to work for George Lucas or somebody, okay, this is the sort of thing that you want to have in your portfolio. Great fun, lots of algorithms in here. Not everything, I think that one of the nice things about actually both of these, but probably more so this one, is that not everything succumbs to an algorithmic solution. Okay, in the real world, in the real engineering world, you don't come up very often with problems and you say, oh, that's a problem to which I can apply this algorithm and it solves the problem. Okay, that's a very naive view of algorithms. Okay, algorithms usually, though, you say, well, I can approximately solve this problem, or here's a heuristic to solve it, and then you can build a good algorithm for that heuristic. Okay, that's much more the way that algorithms work. They're only a piece of the puzzle. Okay, and it's a great toolkit to have good algorithms in your background because it gives you a whole bunch of techniques that you can use to apply to a particular engineering solution to solve pieces of the situation. But in practice, usually things are more complicated. And graphics gives you a wonderful collection of problems, some of which are algorithmically solvable right off the bat, and some of which, well, you know, we don't know exactly, but here's this strategy that we can use, out of which then we build things and we understand, for example, the running time of the thing that we've implemented, okay, or we understand some property of correctness, okay, of the thing that we've implemented, even though maybe we don't have any great understanding of what its running time is going to be, but maybe it works okay in practice. So this is a great sort of combination of real engineering and algorithmic ideas. Okay, so very good stuff. There's another 6852 is a good one. Distributed algorithms. Okay, I'll only spend a minute on this because it's not offered next year. Okay, so this is a course on on algorithms that work in a distributed setting where computers are in different locations, so internet types of algorithms. Okay, how do a collection of machines pick a leader, for example, which turns out to be a fundamental problem in distributed algorithms. How can we, for example, if I had all of you communicating and there are delays and some of you might fail and so forth, and we want to pick a leader, you know, how can we do that in a quick way? Okay, and what do we do when, you know, the group gets partitioned and each subgroup has two leaders? And how does and so forth. And so this kind of study of how is it that you deal with faults, how do you deal with delays and so forth is the topic of distributed algorithms. There's a great collection of topics there, but it's not offered next year, and I think for most of you probably it means that, you know, I think for some of you who are in the MEng and you're juniors now, you probably could catch it, you know, a year and a half hence. Okay, but for those of you who are seniors or not juniors and not going on to MEng, you have to get it some other time. 6854, this is advanced algorithms. And this is offered in the fall. And in some ways, this is the most natural follow-on to this course. Okay, you get into more network flows, solving harder flow problems, linear programming, more on amortization, okay, and a lot of other advanced topics in optimization and so forth. So this is the most natural course to follow on to this course in that it's covering essentially, sort of leading, the trajectory is essentially the same. So if you like the topics that were in this course, okay, then the advanced algorithms course is a very natural one to continue in the same, and in fact these two, 6046 and 6854, are essentially a two-semester sequence for people who are interested in that. But we've generally tried to de-emphasize that because we have so many other courses that can be taken that, you know, this isn't the only one that makes sense to take. There's another one, 6855, which is network optimization. And this is really focused on things like network flow. This is a graduate course taught in the spring. Okay? This is actually not as advanced a course as this one. Okay, this is sort of taught more at the level of this current course. Okay, and it's taught by people in the Sloan School. Okay, because it turns out that the application of network flows and linear programming, et cetera, is a major piece of optimizing how various logistical problems and supply problems and so forth work in the real world. Okay? For example, every farmer these days uses linear programming daily. Okay? Interestingly. Okay? They all have a PC and they all run linear programming in order to optimize various things in the operation of their farm. Things like everything from calculating how much fertilizer to put on their fields, on their different fields based on the current prices of fertilizer, to what plants they should, what crops they should grow from turn to turn. And many of those end up being linear programming. So if you're interested in being a farmer, no. If you're, okay, so the point is that it's wide range of applicability of these techniques, okay? But this is sort of more at a, you know, at a, I think, a little bit lower level than advanced algorithms. Okay. Randomized algorithms. Okay, this is taught next fall. Okay, so if you like probability, this is a hard course. It's probably the hardest of these three. Okay, it's lots and lots of opportunity to understand how randomness helps us compute fast. Okay, and a lot of calculations, you know, Chernoff bounds. So did you learn Chernoff bounds in 6042? Little tails of binomial distribution. Yeah, okay, those kinds of arguments. Ooh, boy, we see a lot of those in this kind of course. Okay, so really, really a fun course, but hard. Okay, fun course, but hard. 6875 is cryptography and cryptanalysis. This is a graduate course taught in the fall. Codes. Okay, you know, how do we make digital signatures? Okay, topics relating to security, although there's a separate security course that doesn't have 6046 as a prerequisite. And sort of the foundations. This requires you learn a bunch of number theory, because it turns out number theory is fundamental to this topic, and number theoretic algorithms. Okay, and so things like greatest common divisor algorithms and algorithms for finding primes and things of that nature. Okay, algorithms for factoring. Okay, such as they are, we don't know how to factor very well. Okay, which is sort of the basis of much cryptography. It's the fact that we don't know how to factor well. Makes things secure. Okay. A course which I'm not quite sure why it's not cross-listed in Course 6, because the professor who teaches it actually got her degree in Course 6, and a lot of Course 6 students take it, so I'm not sure why this never got cross-listed. Introduction to Computational Molecular Biology. Graduate course in the fall. Okay, so if you're interested in applications of computation to biology, this is the course for you. A lot of issues of doing things like string matching, which is a topic we didn't really cover here, but which is covered in the book. You know, how do you match up DNA strands? Lots of dynamic programming, lots of structural issues having to do with geometry. Okay, as you're looking at, say, the formation of virus shells. Turns out they obey very beautiful mathematical rules. Okay, and so you learn some biology here. You learn some computation. Also has some elements of, you know, what's in parallel scientific computing with numerical calculations, because you're interested in physics and forces and so forth. So you know, a lot of interesting topics here, and all of which require all the sort of the basics that we've taught here, and lots of other advanced courses. And in particular, you know, 6046 is a prerequisite for some of the AI courses, for some of the other systems courses. that I'm not going on into because they're not really on the topic of algorithms. These are all have algorithms as a central theme in the course. Okay, you'll see in the catalog 6046 is a prerequisite to huge numbers of things because it's expected that you can do the analysis of the running times of things, that you know that sorting runs in n log n time. You understand what hashing is and when hashing is appropriate. Okay, you understand some amortized analysis. Okay, you can talk intelligently about the running time because a lot of what you learn out of this course is not even the specific data structures and algorithms. It's also the thinking about algorithms and having algorithmic language that you can use to precisely describe what you mean. So when you say something is linear time, that means something, okay, in any of the fields of computer science. In fact, even more and more so outside of computer science. Okay, it means something in terms of what you can expect. Something's linear time, it's generally pretty fast. Okay, thing is quadratic time, takes a while longer. Okay, so these kinds of notions appear everywhere because people are worried about it. If it's exponential time, it's like, ugh. You don't solve very big problems if it's exponential time. Good. So that any questions about other follow-on courses? How many people are likely to take another algorithms course, and how many people? And then I'm going to ask how many people this has really been it. So how many people are likely to take another algorithms class? Okay, a bunch of people. Okay, and how many people think this is it? This was just too much. That's fine. That's fine. Not different strokes for different folks. It's definitely different people have different strengths and different interests and so forth. And so I have no ego associated with people who say, "Phew, glad that's over." I mean, I had the same reaction to classes that I took. There were, when I was doing physics as an undergraduate, it was like, at some point I just said, I like physics, I like the notions in physics, etc., but boy, when they start doing that left-hand rule stuff and precession and so forth, I got no idea what's going on, okay? I like the discrete math and so forth. So, so I'm not a physicist, okay? I appreciate physics, but I'm not, I'm not somebody who's gonna pursue that. Even though I've worked a lot with physicists, actually, in doing parallel computing. They're one of the main people who like to do parallel computing. It's good I had some background in that so I can talk to those people. But not my strong point. Okay, I never quite understood why the sky was blue. So any questions about these courses? Okay, let me, I always like to finish up by telling you one of my favorite algorithms, okay? And this is an algorithm that some of you may have seen, and I always get concerned because eventually you're going to start teaching it in things like 6042, and then you'll all have seen it. This is an algorithm for multiplying on your fingers. So who knows how to multiply on their fingers? Everybody knows how to count on their fingers, right? And adding, right? 3 plus 4 is 1, 2, 3, 4, 5, 6, 7, okay? So you can do it with nines, right? That's a good algorithm. So do you want to explain it? Go ahead.
Put up 2 hands. 9 times 3 is 27.
Right. So you put up your hands like this, and then you say, if you're going to multiply by 3, you put down the third finger, and then what's left? 27. Okay? But this is a more general algorithm. Okay? So this is an algorithm where you can multiply anything from 6 times 6 up to 10 times 10. Okay? And it requires you to add, so you have to know addition. Okay? Okay, and you have to know 1 times 1, sorry, 0 times, 0 times 0 up to 4 times 4. Okay, so here's how you do it. Okay, so we have your hands. Okay, you can see why I didn't become a professor of art. Although my sister is. I mean, she says, I don't understand how this happened. Because she's a painter and a good one, and teaches at an art school in Los Angeles. And you know, what happened to me? So she says that one of her problems is she always is fighting with her left brain. Okay, whereas me, my right brain gave up a long time ago. She at least has a fight going on. Okay. So the idea is, so and you can put up your fingers to sort of see this, okay, is we're going to label these fingers 10, 9, 8, 7, 6. 10, 9, 8, 7, 6. Okay, so like this. And if we want to multiply something like 7 times 8, what we do is we connect those two fingers together like this. Okay, 7 times 8. Okay? And now the way we get our answer is we count 10 for every number up to and including the two that are tested. So count 10, 20, 30, 40, 50 in this case. And then we take the number on the left side here and multiply it by the number on the right side here. So in this case, it's 3 times 2, which is equal to 6. So 50 plus 6 is 56. Okay, so we can try a different one. Okay, try a different one. Okay, what one should we do? I'm going to let you prove this. And remember, everything in lecture is covered on the exam. Okay, so what should we do? Excuse me? 8 times 9. 8 times 9. 10, 20, 30, 40, 50, 60, 70. 2 times 1 is 2, 72. Okay? So one way we could prove it is just do all the possibilities, because there aren't very many. But then I'll say, what happens if we'd all been born with 6 fingers? Does it still work? Okay, what's another good one to do? 6 times 10. Okay, 10, 20, 30, 40, 50, 60. 4 times 0. Is that a great algorithm? Is that a great algorithm? So I've actually done a lot of work on things like arithmetic and multiplication and so forth. In fact, for one company, and this was probably about 15 years ago. No, it was more than that, probably 18 years ago. One of my first consulting jobs. I saved a company $250,000 back when that was a lot of money. With like 10 minutes of talking to them about building circuits, integrated circuits for doing multiplication. So they had this multiplication circuit that they were working on, and they had the following problem, which was that they had been designing it for an integrated circuit process, as it's called, and that process was going to be delayed by 6 months. So they had a choice. They could either wait 6 months, okay, for this process to come online, and then all the circuits would be fast enough for their original design to work, okay, or they could build the circuit in the old process, but the problem was they weren't meeting their spec, and they'd had 2 circuit designers on this problem trying to speed up the individual circuits, making the algorithm, making the matrix multiplication algorithm go faster. Okay, speeding up the addition, speeding up how fast the gates went, optimizing things. They had 2 circuit designers working on it, and the problem was that if they missed the deadline, this was for a government contract, then government contracts have penalties that kick in. And those penalties, if they ended up getting delayed to when the process was going to come out, were going to add up to $250,000. Okay, so this was really, and this was, by the way, so here's a good question. Okay, what do you think MIT offered me as an assistant professor when I first came here? Okay, I interviewed in 1980, I came in 1981, just to get an idea of how big $250,000 was back then. What do you think MIT offered me for my academic year salary? 30 grand. Okay, that's too high. Any other guesses? 20 grand? 25 grand? 25 is too high. 20 is too high. I was offered 19.5, okay, when I came here. That was also the lowest offer I received. But a high offer in those days was like 23 or 24. Okay, so this was like, $250,000 in those days was a lot of money. I make more than that now. Okay, so in any case, in fact, this one thing of 10 minutes of algorithmic consulting made it so that they kept me on board, well after I felt personally worth it. Okay, because their direction had gone off in a way that wasn't particularly, to me, an interesting way to go because of their particular decisions. So in any case, so here's what they were doing. They had a circuit so everybody knows how ordinary matrix multiplication works, right? But of course, on a computer circuit, you're doing it in binary. Okay? And so they had some number, say, okay, and the first thing they do is multiply these things in binary, okay, using the normal algorithm. Then they add up all the partial products. So here, for example, we get 1101, and then we get 1101, and then we get 0000, and then we get 1101, and then you add these up to get the final answer, okay, in binary. Okay? And the way they were adding it up was adding this number to this number and adding the result to this number and the result to this number. And so the time it was taking was linear in the time to add these things up. Okay? So I made the following suggestion. It turns out that actually multiplication in a circuit you can do in order log n time. It's a parallel circuit, and part of parallel computing is understanding how circuits operate, okay, digital circuits operate. Okay, and you can do it in order log n time by essentially a divide and conquer method. It's very clever because you can't if you just try to add two numbers, it still takes you order n time because you have to wait for carries to propagate if you do it in the naive way. But it turns out there's a fast adder you can do. But even if you do that, you get then an order log squared n time algorithm. And it takes a little bit more cleverness. And you can read about it in the book, or you can take one of the more advanced classes to get an understanding of how some of these work. So knowing that you could actually make multiplication go fast, I said, well, how about if instead of adding up all the numbers, you add up half of them, and in parallel add up the other half, and add up the two results. Okay, so they had two designers who've been working on these, full adders and stuff that they use for building this stuff. Okay, so they implemented this, met the spec, no sweat. Okay, just add up half, basically cut the time to run the circuit, theoretically, for this part of the circuit by half, and it essentially brought them below the spec that they needed to do it. Okay, saved them $250,000 for 10 minutes of consulting. Okay, so that's how you get the big bucks. Okay, as you know algorithms. Okay, there's a saying that if you want to be a good programmer, okay, there's only one way to do that, and that is to spend 2 years programming every day. Okay, that will make you a good programmer. Okay, if you want to be a great programmer, there's 2 ways to do it. You can spend every day for 10 years programming, or you can spend every day for 2 years programming and learn algorithms. Okay, so because when you know algorithms, you now have a lot of tools to solve things much faster and much more clever and using reasonable resources than you do otherwise. Okay, let's how about have the course evaluations, and then we'll say our fond farewells until the final exam. So everybody knows the exam got moved. It's no longer in 10250. Okay, it's on the first floor of Building 2, and I think the TA should send out announcements to their individual recitation sections for exactly which room it's going to be in. I think the only complication there may be on which room is for George's sections, which are large and may not fit in his room, in which case will spill over into some of the other sections. Okay. Yes, question? The conflict exam is where we said it would be, which is, where is it? Somewhere. It's on the web page, yeah. It's on the web page. So everybody should check the web page. And if you haven't registered for the conflict exam, please do so by this Friday. Okay, that's also important so that we can get an actual count. Otherwise, we'll be expecting you at the regular exam. So it's been my pleasure to teach you this term. Enjoy filling out the getting back at me, which is, I think, the right things for students to do at these times, to let all the anger and frustration out. Okay, and let us have it, because I think without accurate feedback, the courses just don't get any better. And it's a little bit of altruism for people who come after you. And hopefully other people will be doing that for you in the courses you have yet to take. So thank you very much.
Yeah, thank you also. It's been great having us students.
And I hope everybody does well in the final. I always, I root for the students, I'll tell you. I was a student myself, and it was not pretty. Okay, I was not the world's best student at that time. Okay, I had a real rough time. So I really empathize with how hard it is to be a student, and it's also very easy to be a student. And that's sort of the conflict. Is there's some things that are very easy, there's some things that are very hard, and the hard things have a lot to do with self-discipline and internal reorganization of yourself as you move, as you learn to cope with full adulthood, which you didn't have to do in high school. So it's hard being a student. There will be a review session. Good. Review session will be next Monday night from 7 to 9 in this room. Okay, and it'll be basically going over the things that are on, that we've done in the term, making sure there are no questions about how things work, and some review of some problems from other for other final exams. Okay, so for people who would like to attend that, it's optional. 7 to 9 next Monday. Okay.